Today, we will be learning about quaternions. Let's start with something familiar. A normal number lives on a number line. Examples include 3, -5, and 10.2. These numbers only need one value to specify their position. They tell us how far and in which direction we move along a line. Later, mathematicians invented complex numbers, which added a new direction called I. A complex number consists of a real part and an I part. For example, 3 plus 2i and 1 minus 4i are both complex numbers. Complex numbers allow us to describe things that ordinary numbers cannot. One of their most useful properties is that they can represent rotations in 2 dimensions. Using Euler's formula, a complex number with length 1 can be written as cosine theta plus I sine theta. When such a number is multiplied by another point on the plane, it rotates that point by theta degrees without changing its length. This makes them extremely useful in mathematics, physics, and engineering. After discovering this idea, mathematicians then asked, can we create something similar for rotations in 3 dimensions? The answer to that question is quaternions. A quaternion is a number that contains 4 components instead of 2. A quaternion can be written as Q equals A plus B I plus Cj plus dk. Here, A represents the real part, while B, C, and D represent imaginary components. For example, 1 plus 2, I plus 3, J plus 4k is a quaternion. Thus, a quaternion needs 4 numbers to describe it completely. Another way to think about a quaternion is as a collection of 4 values. For example, this quaternion can be represented as 1, 2, 3, 4. The first value is the real part, and the remaining 3 values form the vector part. This vector part behaves somewhat like a 3-dimensional vector. To understand quaternions better, we need to understand I, J, and k. For complex numbers, I multiplied by I equals -1. Quaternions extend this idea by introducing 3 imaginary directions instead of 1. These directions are called I, J, and k, somewhat similar to axes in 3 dimensions. They follow special multiplication rules that make quaternion rotations possible. The first set of rules is very simple. These 3 rules resemble the familiar complex number rule involving I. However, quaternions also include these sets of rules between different imaginary directions. These relationships connect the 3 imaginary directions together. Here, the order matters. For example, I multiplied by j equals k. However, j multiplied by I equals -k. The result changes when the order of multiplication changes. This behavior is called non-commutativity. Using them, instead of storing a rotation using 3 separate angles, we can store it inside a single quaternion. Now, let us see how a quaternion rotates a vector. Suppose the vector is 1, 2, 0. This vector points somewhere between the x-axis and y-axis. We want to rotate this vector by 90 degrees around the z-axis. Before using quaternions, let us think geometrically. A 90-degree rotation around the z-axis transforms every point in the xy plane in a predictable way. The x-coordinate becomes the negative of the original y-coordinate. The y-coordinate becomes the original x-coordinate. The z-coordinate remains unchanged. Therefore, we already know that rotating 1, 2, 0 by 90 degrees around the z-axis will give the rotated vector -2, 1, 0. This gives us a target answer to verify. The first step is to specify the rotation angle. Our desired rotation is 90 degrees. However, quaternions store only half of the desired rotation angle. Therefore, instead of 90 degrees, we use 45 degrees inside the quaternion. The second step is to specify the axis of rotation. We want to rotate around the z-axis. The z-axis can be represented by the vector 0, 0, 1, or k. This axis tells us the direction around which the rotation occurs. Every quaternion rotation needs both an angle and an axis. Now we build the quaternion Q describing the rotation. Just as complex numbers use Euler's formula to represent rotations in 2 dimensions, quaternions use a similar idea to represent rotations in 3 dimensions. In fact, a quaternion rotation can be represented using cosine of half the rotation angle plus sine of half the rotation angle multiplied by the chosen rotation axis. So here the quaternion is equal to cosine of 45 degrees plus sine of 45 degrees multiplied by k. This becomes 1 over root 2 plus 1 over root 2k. The rotation operation is described using this formula, where this v prime is the new rotated vector. Next, this term q bar is the conjugate of the quaternion q. The conjugate quaternion is obtained by reversing the sign of the vector part. Therefore, the conjugate becomes 1 over root 2 minus 1 over root 2k. We now have everything needed for the quaternion rotation. The only remaining step is to convert the vector v into quaternion form. Then we can perform the rotation operation. The vector 1, 2, 0 becomes the pure quaternion I plus 2j. Notice that there is no real part, only the vector part is present. This is called a pure quaternion. We now perform the rotation by multiplying q with v, followed by q bar, and using these set of rules. After carrying out the quaternion multiplication, the result becomes minus 2i plus 1j. Converting this back into vector form gives minus 2, 1, 0. This exactly matches the answer predicted by geometry. Programmers love quaternions because they are efficient. A rotation matrix requires 9 numbers, while a quaternion requires only 4. The motion in games remains stable and continuous throughout the animation. This smooth behavior is one of the biggest advantages of quaternions. Another advantage is the avoidance of gimbal lock. When rotations are described using pitch, yaw, and roll, 2 rotation axes can sometimes line up. When that happens, 1 degree of rotational freedom is lost. The object may suddenly behave in unexpected ways. Quaternions avoid this problem because the entire orientation is stored as a single mathematical object. For these reasons, quaternions are heavily used in video games, robotics, drones, spacecraft, virtual reality systems, and computer graphics applications. If you enjoyed this video, please don't forget to like, share, and subscribe to our channel. Also, you can support my channel by joining our community and becoming a member. So good!